We have recently started Chapter 10 on gases. In the first two sections, we described properties of gases and how they are different from those of solids and liquids. And we've also discussed pressure, the fact that pressure is created by gas particle collisions. And we've also talked about how to measure the pressure of a gas sample using a manometer and how to measure atmospheric pressure using a barometer. Today's section is about gas laws and how the variables of temperature, pressure, volume can impact each other if one changes. Before we get started, make sure you have the following items available: your gas laws pre-test, your notes handout, lecture examples handout, and a calculator. Previously, you should have completed the gas laws pre-test 10 questions. So if you haven't done these previously, make sure you take a moment to do those before we get started. Question 1. A metal cylinder contains 1 mole of gas. What will happen to the pressure in the cylinder if another mole of gas is added? And the correct answer is it should double. If there are more particles present, they should create more collisions and your pressure should go up. And since you're actually doubling the number of particles and collisions, your pressure specifically should double. Question 2. A child sits on a partially filled balloon, decreasing its volume by 1/2. What is the new pressure inside the balloon? The correct answer is B, twice as much. If the balloon gets smaller in space, there's less space for those particles to collide, so they should collide more frequently, and the pressure should increase. 3. If a sample of gas is heated, what happens to the pressure? Well, as the gas particles absorb heat, they should move more frequently and collide more frequently, and so the pressure should go up, increases, D. 4. For a fixed volume of gas, as temperature decreases, pressure blanks. So if the temperature goes down, that means the particles should slow down, they should collide less frequency, and the pressure should decrease. Sorry if you put letter D, that's actually not the way it works. 5. Whose gas law states that when volume increases, pressure decreases? This is a picture of Boyle. It's letter C. 6. What temperature unit must be used when working with gas law equations? We will talk about that a lot today. That needs to be, the units need to be in Kelvin, D. 7. Fred the chemist takes a balloon outside on a very cold winter day and its volume decreases. When Fred returns inside, the balloon expands to its original size. Why does the balloon expand as it warms up? And I know there's another outlier there. D is not the answer. But if you've been in my room and it's been cold, well, I can understand why they'd be excited if they're finally warm. However, the correct answer is A. As those gas particles absorb the thermal energy and they move more rapidly, they'll push on the walls of the balloon and it will expand. 8. The pressure of a gas is blank to the temperature if volume is kept constant. So we're talking about pressure and temperature. B, they are directly proportional. 9. This graph can be described as A, inversely proportional or inversely related. 10. This graph represents the relationship between B. This is pressure and volume. If one goes up, the other goes down. To help us understand gas laws a little bit more, we are going to take a look at this gas law simulator. So here's the simulator, and you can see there is a chamber for gas particles. There's a little dude over here that'll help us change the size of our container, or the volume of the gas. There's a temperature gauge and a pressure gauge. We can add or remove heat, and then we can pump the handle to introduce some gas species into our container. So we'll start with just putting some gas particles in there. Notice right now, before we add any, the pressure is 0. So as the particles collide, we see that the pressure climbs. It should stabilize at some point at close to, well, it looks like a little over 2 atmospheres, and it's around a temperature of 297 Kelvin. You should think about what you would expect to see happen if I add or remove heat. And so if I add heat, the particles should move more, they should collide more frequently, and the pressure starts to go up. Not too crazy though. We better cool it down quickly. I think we got it in the nick of time. And notice the reverse happens if we cool it down. The particles slow down, they collide less frequently, and our pressure should drop. You can see we can really cool it down to quite a low temperature, and you can see they do slow down considerably. So now it's back at 0. We're going to, let's see, reset, maybe add a couple pumps again, or 3, and take a look at a different variable. So if we have this little helper person here on the side that can make our container either bigger or smaller, we should see a change in the number of collisions as well. So if I allow the container to be made bigger, there's more room, the particles will not collide as frequently, and we should see kind of the pressure drops. However, if we force the particles closer together, if I make the container smaller, we should notice collisions happen more frequently and the pressure goes up. There's a lot more friction, the temperature goes up. Eventually, the container will not be able to withstand the pressure and it will blow off. So some kind of common sense observations that we would expect to see with these different variables. So now let's talk about some different gas laws. Very important that for all gas law equations, you have to use Kelvin temperature. This is such an important point. Kids that forget to change this temperature really end up losing a lot of silly points on a test or on a final, which is really just unnecessary. So I tend to not even write my temperature in Celsius. If I see it in Celsius, I automatically add 273 to convert it to Kelvin. We're going to start with some different gas laws, and most of them are a combination of 2 variables. The first one we're going to look at is Boyle's Law, named in honor of Robert Boyle. And I look at that hair and I'm thinking, it's got to be a wig. Those ringlets are just too perfect. There's no way anybody's hair is that perfect. Anyway, Boyle's Law tries to show us a relationship between pressure and volume. And this is the statement of the law. The volume of a fixed quantity of gas at constant temperature is inversely proportional to pressure. And with all these gas laws, there's a statement and then there's a corresponding equation. And it's important to have all these equations in your notes so you can easily find them. In this case, P1 V1 equals P2 V2. And your pressure units can really be any of the ones we talked about. Millimeters mercury, torr, atmospheres, kilopascals, as long as they're the same on both sides. I would say the same thing about the volume. They could be in either milliliters, or in liters, or in cubic centimeters. Any of those are fine, but they have to always be the same on both sides. It's good to also, these demos that are mentioned, we will be kind of reviewing in class. The list is just there to remind you later of demos that give a good example of these types of gas laws. So Mr. Balloon and a bag of chips, we'll see those later down the road. Here's also a graph that shows the relationship between pressure and volume as well, inversely related. And if you haven't been in a math class for a while, although I know most of you have, an inversely proportional relationship is where one increases and the other increases, or other decreases. They go in opposite directions. Then we have Charles' law. Charles is temperature and volume. And this is a directly related set of variables. So the volume of a fixed quantity of gas at constant pressure is directly proportional to temperature. I mean, a great example, if you think about this one, we always say that gases expand when heated, or they contract when cooled. We had the liquid nitrogen demos earlier in the year, and we saw that when you put a balloon into that liquid nitrogen, the particles slow down so much, the gas really slows down. There's not as much pressure pushing out on the balloons, so the balloon shrinks. And then when you take it out of the liquid nitrogen, it reinflates, and it goes back to its original size. Now, the last law was an inversely proportional, and it was PV equals PV. This is a directly proportional or directly related law, so it should not be TV equals TV. Instead, this one is V over T equals V over T. And you may want to make a note for yourself here. We have to make sure that these temperature variables are in the units of Kelvin. A directly related graph looks very different than the one we saw previously. As one variable increases, the other increases. The last combination that we'll see is temperature and pressure, Gay-Lussac. And this is another directly proportional or directly related set of variables. If temperature goes up, pressure will go up. There is a reason why on the side of aerosol cans, it says do not puncture or incinerate. Incinerate means to throw something in a fire and try to burn it. That aerosol can, if you throw it into the fire, the gas particles are going to absorb that heat. They're going to move so much faster and build up so much pressure that you could have a bomb on your hands, and that's definitely a dangerous situation, so keep those aerosol cans out of the fire. You should think to yourself here, if we have another directly proportional set of variables, whether you think it will look like Boyle's law, PV equals PV, or Charles' law, V over T equals V over T. And hopefully you would recognize that it should have the same form as Charles' law. So this one is P1 over T1 equals P2 over T2. And again, make sure as you use this equation, your temperature is in Kelvin. Another directly related graph as well. The combined gas law, it's sometimes helpful to put all three variables into one equation because sometimes pressure and volume aren't the only thing changing. Maybe the temperature's changing as well. And so if all three variables are changing, then we use this form of the gas laws, which takes Charles, Boyle's, and Gay-Lussac and rolls them all into one law. Now, this top form of the equation can sometimes be confusing for kids to use, especially if they end up solving for, let's say, T2, which is in the denominator. So if we get those out of the bottom and we multiply both sides by T2 and both sides by T1, the T1 will end up over here, the T2 will end up over here, and we get this form of the equation as well. So it's fine to use either one. I do think kids sometimes have a little better success using the second one. So we've got some examples to go through, and I'm going to show you for the first one how I would go ahead and work through it and show my work and list my variables, and then once I've done this one, you can pause the video and try the second too. So this example says a hot air balloon is filled with 725 cubic meters of air at 1 atmosphere. What's the volume of the balloon when it rises to an altitude where the pressure is only 0.35 atmospheres? So when I look at this one, either you should be circling or underlining the variables in the problem, or you should take time to write them. So I sometimes have kids that will, take a look at this problem and they see 725 cubic meters. You have to recognize the labels and what they represent. That is an amount of space. So my V1 is 725 cubic meters. My pressure is 1 atmosphere, that's P1. It says, what is the volume? So V2 is my question mark. And then I know 0.35 atmospheres is my second pressure. Dr. Hansen is always very, very good about providing equations for us. However, you have to know the proper equation to use the proper time. So if we look at what we've identified in this problem, 2 pressures, 2 volumes. And so P1, V1 equals P2, V2, which is Boyle's law. So 1 atmosphere, 725 cubic meters. The second pressure is 0.35 atmospheres. And you can either put X or V2, either one. If you go ahead and solve, we should get a volume of 2,100 cubic meters. And if you think about the change that this problem is going through, or the situation, I guess, that's changing, the pressure is dropping. So there's less pushing on the outside of this hot air balloon. And so if there's less pressure pushing on it, the same amount of pressure is pushing out from the inside. So as the pressure on the outside drops, the balloon, we should expect that it will expand. And if you compare what it started at for a volume compared to what it ended at, we do see that come true in the numbers. So at this point, I would pause the video, complete examples 2 and 3, and then resume the video so you can check your work. All right, hopefully you've had a chance to do those calculations. Example 2. It says a balloon inflated in an air-conditioned room at 27 Celsius has a volume of 4 liters. It's heated to a temperature of 57 Celsius. What is the new volume? As I mentioned earlier, you absolutely must change your Celsius temperature into Kelvin. And so I tend, if I want to list my variables, I try not to ever list them in Celsius, because then I might mistakenly use them in the problem. So temperature 1 is 27 degrees Celsius. If I add 273, that would give me a temperature of 300 Kelvin. And that 27 plus 273, it is significant to the ones place, so I am going to put a little decimal there to make sure it shows that there's 3 sig figs. My initial volume is 4 liters. I want to know what the new volume is, and my new temperature, it has gone up from 27 to 57, so that will be 330 Kelvin. 2 V's, 2 T's, means we're looking at Charles' law. V1 over T1 equals V2 over T2. So, let's see here, 4 liters over 300 Kelvin equals V2 over 330 Kelvin. If we're solving for V, it's cross multiply and divide. So V2 would be 4.40 liters. Again, temperature goes up, the molecule should move faster, and the amount of space they move within should expand. So we should see our volume increase. Last example, I referenced throwing an aerosol can in the fire earlier, and that's never a good idea. Let's take a look at this situation. If you read the problem, it says that the original pressure is probably what it's close to in our classroom right now, 1 atmosphere, at a temperature of 24. Well, 24 plus 273 is 297 Kelvin. It asks what the new pressure is. What is the internal pressure of that gas when the temperature reaches 927? So T2, if we take 927 and add 273, we should get 1200 Kelvin. So our third equation, Gay-Lussac, P over T equals P over T. If we substitute those numbers in, we have 1 atmosphere over 297 and P2 over 1200 Kelvin. Again, cross multiply and divide. The pressure should work out to be 4.04 atmospheres, which is over 4 times what the pressure normally is in the room. So it's not, if that's the amount of pressure inside that aerosol can, there's no doubt that it will definitely explode if you throw it into a fire. Now, one last thing I want to show you about the combined gas law. So in the combined gas law, PV over T equals PV over T. One of the handy things about knowing the combined gas law is that you can obtain any of those other 3 gas laws from this equation just by holding one of the variables constant. So for example, Boyle's law, sorry about that, pen's not working here. Boyle's law is pressure and volume. So that means temperature is not changing. So if I eliminate temperature from the combined gas law, I get, lo and behold, Boyle's law. If, on the other hand, let's say, eraser, work with me here, I want Charles' law, which is temperature and volume, then I eliminate the pressure from the equation, and voila, I have Charles' law, V over T equals V over T. Now kids tell me, well, that's great, but I don't know which person is which combination of variables. So here's one way to do it. Charles in Charge used to be a TV show, or Charlie's Angels a long time ago used to be on TV. So Charles was on TV. This next example is a bit disgusting, but Boyle's law is pressure and volume. And this, I had a student that suggested to me, they came up to me on the side and said, they're like, you know, think of a boil. You know, boils are like these gross, pussy, pimply things. And he said, you know how those pimples, like, they're just so gross, they're just ready to pop? You could say they're particularly volatile. And I was like, that's disgusting. I guess it works. I usually like to use instead that Boyle played volleyball. It's just a little less disgusting. And then the last combination of letters would be Gay-Lussac, and people say that he used to go around TPing people's houses, and so that would work for that combination of variables. So that's it on our discussion of gas laws. If you have questions, please email me or see me. Have a great day.